It's 8 a.m. Pacific time. It's time for us to get going. Welcome to tinyML Talks. Today it's September 26th. Today we have Ilya Gozman. He's our guest joining from Grovety .ai, where he is a senior fellow and also a chief AI architect. The title of his presentation will be minimizing resource usage in microcontrollers for cost-effective solutions. Before we start, let me acknowledge our strategic partners and sponsors. So we have a big group of people who are active members and companies, active members in tinyML, and they are our strategic partners: AZIP, Analog Devices, Adreno, ARM, BrainChip, Edge Impulse, Efficient, Greenwave Technologies, Grovety Inc., where Ilya works, Hymax, IBM, Imagimob, Infineon, Inotera, Microsoft, Nokia, NXP, Poland Technologies, Kixo, Qualcomm, Renaissance, Schneider Electric, SensiML, Sony, Silicon Labs, ST Microelectronics, Synaptics, Syntiant, and TDK. Thank you all these companies for supporting tinyML and making these events possible free of charge. As usual, we would like to promote our fast-growing communities. You can join them on meetups. We have around 17,000 people there in 41 countries, almost 50 groups. And likewise, the LinkedIn community is also quite active with close to 17,000 people there. So, and you can join them, the QR codes are there. So these presentations will be available on YouTube as usual this week. And you can subscribe to the channel. It has over 10,000 subscribers, a lot of videos, a lot of views there. And the QR code is also there. So once subscribe, you'll get notifications on new videos and new information there. So in addition to meetups and virtual events, we also do in-person events. We had tinyML Summit back in March, then European event in June, European, Middle East, and Africa. And in about 6 weeks, 7 weeks, we'll be very happy to host tinyML Asia, a technical forum. It will take place in Seoul, in South Korea on November 16. So registration is open. We have a program on the website. I think the timeline for submissions has passed. We have a very strong program there for this event, so please go there, take a look, and register if interested in attending. Again, this will be in-person event. I think next announcement we have is on 2023 AGI report. So we've been working with Wolfer on this report, and it's been quite successful, close to 10,000 downloads for this report in the past, I would say, 2 months. It's been very popular, and you can download it also free of charge. It has a lot of information on Edge AI and tinyML. I think this report contains 117 pages, if I'm not mistaken, and it covers all the aspects: technologies, applications, algorithms, models, software, everything. So. And as a preview or as a heads up, I just had a meeting with Wolfer. We are launching a campaign for the 2024 report. That will be a new report because the field is evolving very fast. And this report will also have more contributors, more companies, and kind of more up-to-date information there. So the 2024 report is going to be available in April of next year, just before the Embedded World 2024. So again, you can go and download it there, and it's actually a very nice report to read. Ilya, he's been with Grovety for quite some time, and he's currently a senior fellow and the chief architect there. And he started from a developer, and he became an expert in this field, and he is actually developing a lot of interesting technologies in this space. Specifically, I think one of kind of his strengths is in the compiler area and chip architecture, including LLVM and TVM optimizations. And I think compiler is a very, very important area these days, especially. And other projects he's been involved, like video processing and IP cameras and so on. So formally speaking, he received his master's degree in applied math and computer science in 2017. And very happy to have you here, Ilya. So the stage is yours.
Yeah, thank you, Evgeny. Hi, everybody. So I'm Ilya Gozman, Chief AI Architect from Grovety. And in this presentation, we will tackle the core challenge in tinyML, minimizing resource utilization in microcontrollers for cost-effective solutions. The spotlight will be on the fine-tuning strategy, an approach that plays a critical role in optimizing neural network inference. We will illustrate how Apache TVM, an open-source machine learning compiler, significantly aids in reducing device cost and energy consumption. We will also discuss our choice of micro TVM and ARM SSU55 on the Alif Semiconductor E5 SoC by detailing their unique advantages, how they align with our goals, and revealing the results of our optimization efforts. Finally, we will provide an exciting sneak peek into the future of our tinyML efforts to further refine networks while maintaining accuracy and our innovative strategies for ongoing optimization and development in tinyML field. We took the words from the 2023 AI Technology Report, which was released in the summer, and for our point of view, the most current and most comprehensive source in the HAI and tinyML areas. HAI benefits and challenges are doubly relevant to the narrower technology, tinyML, memory, latency, power consumption, and so on. But the biggest challenge right now for tinyML applications is minimizing resource usage in microcontrollers. We are just seeing the tip of the iceberg now, said Shay Kevin Brown, Director of Products Marketing at Synaptics. When working with pre-built models, various modifications can be applied to enhance performance and adaptability. One such potential modification is network compression, which can be performed through pruning and quantization processes, which reduces the model's complexity and size. Another potential modification is simplifying unsupported operations to basic primitive blocks, allowing for broad application compatibility and usage. Network layers can also be modified by transforming and merging them to streamline the model structure and optimize the resource-intensive layers. This can help in enhancing the model's efficiency. To minimize the time taken during inference, it is crucial to utilize hardware-specific acceleration instructions. This allows the model to leverage the inherent capabilities of the hardware, leading to faster and more efficient processing. Optimizing the schedule of operation flow is essential in reducing the memory requirements of the model. Additionally, storing model weights in external storage can be an effective strategy to further lowering the memory demands, thus enabling the deployment of models on devices with limited memory capacity. Enhancing energy efficiency is paramount, especially in systems with limited power resources. This can be achieved by moderating the operating frequencies of the MCU and NPU, which allows us to leverage the benefits of heterogeneous systems, thus allowing for the optimal use of varied resources and implementing intelligent power management strategies. These steps ensure sustainable and prolonged operation, even in power-constrained environments. There are two primary approaches in addressing the resource management challenges in tinyML. Firstly, minimizing the cost of developing algorithms, speeding up software development, and eliminating specific AI skills needed. Second is focus on reducing the cost of devices. Costs are a critical challenge that can impact the decision-making process for businesses. Our clients tell us We wanted to find out what benefits the use of neural networks give us. So we choose to use cloud services. Or we plan to sell tens or hundreds of millions of devices. So we need a minimum price for the device. Each approach solves its own problems. So we begin with a predefined neural network model. After that, we apply common enhancements and carry out optimizations tailored specifically to the network's architecture. Then we begin rolling the fine-tuning cycle. The steps of the cycle are, first is implementing granular low-level adjustments using the capabilities of TVM to improve the model's compatibility and efficiency. The compiler then assembles the updated firmware. It is worth noting that our expertise allows us to delve deep into the compiler's intricacies, making corrections as needed. For example, we performed adjustments on the memory access latency specifics in ARM Villa to improve access times. Once compiled, we seamlessly deploy the model on our target device and ensure it operates in real-world conditions. Our robust CI system, acting in the capacity of a profiler, becomes instrumental. It meticulously captures the metrics related to inference behavior, resource utilization, and the overreaching accuracy of the model. Guided by the insights from these metrics, we feed back this new data into the fine-tuning stage. This iterative approach ensures that we continually refine the model and drive towards achieving our targeted performance criteria. For our solution, we require the maximum level of control available over all processes. So we define the following objectives for our CI system. Measure inference speed, memory consumption, and energy usage. Monitor the behavior of network inferences in response to introduced changes or edits. Recompile automatically based on timer, component toolchain updates, and repository commits. Utilize hardware from Alif with Cortex M55 and NPU SoC-U55, as well as ARM Cornerstone 300 simulator. Catalog results for change tracking. In our firmware development efforts, we have utilized multiple tools in the experimental phase. This allows us to be at the forefront of new methodologies. The community around these tools may be emerging, but it's also uncharted territory, allowing us to set benchmarks. The SDK presented us with a more hands-on approach, where understanding its functionalities became an integral part of our development process. We plan to continue developing our evaluation platform to focus on detailed neural network inference. Our goal is to collect the performance and memory usage statistics of each neural network layer individually. Such information will make it possible to perform a more comprehensive analysis. This tool will give us more precise optimization and an enhanced fine-tuning methodology. We value TVM for its ability to provide precise control of a model translation, so we can make precise changes and observe the results of these modifications. Furthermore, we actively participate in the community, promoting collaborative development. Here we see the TVM pipeline for ARM SoC-U55. The relay graph, as loaded from the TVM's frontend, will be partitioned into subgraphs with the creation of external relay functions that could be offloaded to the NPU. In the partitioning stage, we can adjust the behavior of relay optimization passes or add new ones. For example, we could restructure layers so they can be considered as candidates for offloading further. The next stage will allocate such functions to SSU NPU hardware primitive operations. These operations are defined as tensor expressions, closely described for the compute of each primitive operation that the hardware can natively execute in their own relay operators. They represent a pattern of conventional relay operations that are executed atomically in the hardware. Then tensor expressions representations belonging to the offloaded functions will be scheduled to the tensor IR prime func which describe the intermediary storage and hardware operations to execute. Here we can introduce additional T and TIR passes to make the NPU compiler perform memory and performance optimizations. The weight encoding is performed here also, and is represented in the TIR prime func with spot encoding sizes as buffers. We can also tune the process of determining the sizes of buffers and establishing the order of their allocation and usage, which impacts the amount of memory used. One final step, the ARM Villa compiler's backend Python APIs convert the TIR prime func to a command stream, which will be wrapped in a C source that will invoke it using the driver APIs. For our solution, we choose Alif Semiconductor's dev kit with microcontroller class SoC, including Cortex-A, Cortex-M, and SSU55 cores. The Alif Ensemble family includes E1, 3, 5, and 7, which scales from single ARM Cortex-M55 MCUs to a new class of multi-core devices, fusion processors, that blend up to 2 Cortex-M55 MCU cores, up to 2 Cortex-A32 NPU cores, capable of running high-level operating systems, and up to 2 SSU55 micro NPUs for AI and ML acceleration. So the ARM SSU55 significantly enhances the machine learning inference capabilities of microcontrollers, offering performance improvements ranging from tens to hundreds of times compared to Cortex-M, while maintaining low energy usage. It is capable of accelerating specific quantized machine learning operations, including 2D convolution, depth-wise convolution, pooling, and element-wise operators. The SSU55 utilizes the existing system SRAM and flash storage and is equipped with high-efficiency, high-performance Mach engine. During our work with Alif Ensemble dev boards, we aim to get benefits by using 3 power regions. The always-on region is for basic functions, such as supporting the backup SRAM state of the controller in standby mode. The high-efficiency region, the region is where we perform tasks we don't require high performance to save power and extend battery life. The high-performance region is where the device provides maximum performance for specific tasks invoked only as required to conserve energy. The board has 9 power domains, each with its own controller, which are managed by high-level logic to optimize power efficiency based on the device's dynamic performance needs. Alif provides a powerful tool, Alif Conductor, which allows us to configure the board for specific tasks and usage scenarios. One more advantage of our fine-tuning platform is the ability to repeatedly measure the power consumption of every step of the model evaluation workflow, such as awaiting data acquisition, pre-processing, inference, either on NPU or CPU, and post-processing. One of the key performance optimization strategies is to offload as many operations as possible to the NPU. We have introduced a convenient mechanism in TVM for tracking the distribution of each operator among multiple targets. This mechanism allows us to quickly analyze a large number of models and group them based on operators that aren't offloaded. It helps us identify the reasons behind this and find optimal solutions to enhance performance. One of the examples is a group of pooling operations with high stride values. These operations are not supported directly by the SSU55 NPU, but we noticed that most models which have this issue are using kernels with the same shapes as the inputs. That means that stride parameters are not going to have a significant impact on actual operation. So we decided to add an additional check to see if kernel and input feature map shapes are equal. For these cases, we were able to simply change the stride value to 1 to allow the operation to be offloaded to the NPU as usual pooling operations. The benefits of this were 25% inference speedup and 17% of ARM ML models were affected. Another issue we have found during one of our investigations was the lack of support for the part operation over channel access in some micronet networks. This operation appears multiple times and requires the model and the inference flow to switch back to the CPU for this simple operation, which generated huge overhead. We decided to solve the issue by replacing the part over channel operation, which is not present on the NPU, with a combination of identity and concat operations during the allocation step. One limitation of this approach was that we had to keep a paired operation over width or height dimensions, which could be offloaded to the NPU directly. This required an addition of the specific pattern for new part over channels. Finally, all these modifications showed a greater reduction of the inference time. For some models, the speedup can be as high as 400%. But why do we want all the separators to be offloaded to SSU? In the vast majority of cases, operations on the NPU are executed faster. There are many inefficient overheads when switching between the NPU to the CPU and back again to the NPU. For instance, according to our measurements on the Cortex-M55 core, running at 160 MHz, this process takes about 60 microseconds. What we need to solve this is a relay. First, we need to dissect relay and understand what can be optimized. However, an operation won't be represented by just a single line. For instance, a convolution consists of the convolution itself, an offset or bias, requantization operation, and they can be optionally paired in before the operation, or an activation function with clipping. To combat this, we will use a pattern when we need to obtain the parameters of the operation and ensure it meets the hardware limitations. Only after that, we will convert it into one or more ARM-Villa API calls. On this slide, you can see that 3 separate part, const2d and minimum operations translate to 5 TVM relay IR operations. These are mapped to the NPU pattern for conf2d. This means this series of operations can be replaced by a single operation on the NPU. Such an approach not only reduces the size of the command stream, but also speeds up the entire model. The latest results are visible on the graphics presented here. We can see that neural network inference is improved with equal or lower memory and power consumption. Let's delve into some results from specific models. In our work with TVM, we've always used TF-Lite and ARM-Villa as our reference points, as a benchmark compiler for SSU. To this end, we have set our benchmarks against them for a comprehensive comparison. It's important to note that in some instances, performance enhancements come with a trade-off of increased memory usage, as observed in the case of the last network on the slide. This occurred because we needed to block the remove concatenates pass under specific conditions in TVM, which were necessary for this particular implementation. Moreover, we are proactively engaged in MLPerf benchmarking process, presenting performance estimations tailored for the SSU platform. You can look forward to our results in the upcoming iteration. In conclusion, based on our experiences, the milestones we've reached and the progress we observed while tuning these networks, we are deeply confident in TVM's potential as a definitive tool for implementing fine-tuning strategies. Thanks to TVM tools, we can vary networks' behavior, either for acceleration, which requires more memory, or conversely, using less memory, resulting in longer processing times. We would like to acknowledge the remarkable work of the MIT Hardware AI and Neural Nets Lab in accelerating deep learning computing, and specifically the agreed research for on-device training, in which they propose an algorithm system co-design framework to make on-device training possible with only 256 kilobytes of memory, a tiny training engine, which is available on GitHub for experiments. For algorithms and associated tools for on-device tiny learning, we also want to express our profound appreciation to ST Microelectronics and especially Daniel Pao for his great presentations regarding on-device learning and reservoir computing areas. Investigating algorithm-level techniques to reduce memory footprints of neural networks. We want to appreciate the work enabling large neural networks on tiny microcontrollers with swapping to execute neural networks out of core with full accuracy and generality. Based on our experience from these materials, we have identified the following challenges and methods to address them. Per-layer analysis involves a detailed examination of each individual layer within a neural network. This is crucial for understanding the computation and memory requirements of each layer. Evaluating computational requirements requires understanding the number of operations that each layer needs, which in turn helps in estimating the overall computational load of the model. Similarly, analyzing the memory requirements is crucial as each layer has its own set of parameters, such as weights and biases, and intermediate outputs that need to be stored in memory. This analysis can guide memory allocation to help develop optimization strategies effectively. Additionally, the understanding of how data flows between layers is fundamental in optimizing memory usage. For instance, some layers allow for operations that can override the inputs with the outputs, thus saving memory. Latency, the time taken for data to pass through each layer, is another crucial aspect to consider, as it affects the overall inference time of the model. By focusing on the characteristics and requirements of each layer, per-layer analysis can provide valuable insights that can be used to optimize the entire model. With our understanding of the intricacies of contemporary neural network architectures, we have laid out plans to efficiently manage memory. Our upcoming strategies involve transitioning the extensive network weights to external memory. We believe that this will optimize the inference process and streamline our fine-tuning approach. This idea is to dynamically swap chunks of network weights between the device's SRAM and external flash storage. This allows for the deployment of large and complex neural networks without compromising on accuracy. While this approach does introduce additional read and write operations, modern flash storage technologies are robust enough to handle this without significant overhead. Moreover, the slight increase in energy consumption is often outweighed by the benefits of being able to run more complex model. In the context of tinyML, the significance of on-device learning is paramount. It denotes the capability of machine learning models to learn and adapt directly on the local device, eliminating the need to send data to a cloud for training. This let us focus on quantization, aware scaling, and sparse update techniques. The integration of these refined techniques provides a cohesive and adaptive approach to optimizing low-bit quantized neural networks, addressing challenges and offering solutions suitable for resource-limited environments. Optimizing multiple networks with the Alif platform poses a significant challenge: the interconnection of multiple networks while preserving latency, energy consumption, and accuracy. We believe that having multiple networks on a single chip is the future. Multi-accelerator execution can provide unique benefits, especially for computing systems with limited resources. By enabling collaborative and concurrent execution on different accelerators, each with varying performance, energy, and latency characteristics, we can address specific tasks to their own power consumption level. We are currently implementing this approach in our project on a smart camera trap, which we discussed recently at the ARM Tech Talk event. We want to express our gratitude to ARM for the SSU architecture. We truly enjoy working with it, thanks to abundant documentation and the supportive community. After getting acquainted with these neural accelerators, our perspective on edge AI has significantly transformed, unveiling new possibilities. We are looking forward for the continued evolution of this field. Great job, guys. Of course, everything we have discussed needs to be tested in experiments and real-world applications. Here you can find useful resources which inspired us and which we use. Thank you for attention. I'm ready to continue further communication in questions and through my email.
Well, thank you, Ilya. I think it's a very interesting presentation on actually a very interesting and important topic, because I think on-device learning, I think it's a future of this edge type of devices. Yeah, I'm curious, and actually what you show, kind of doing it on 256K of memory, that's actually pretty impressive. And before we open floor to questions, just a question for myself. From your experience with kind of working with ARM type of devices, what do you think should be an ideal hardware configuration for on-device learning type of devices? Because right now it's all digital, and but people have been talking about doing some neuromorphic for on-device learning. Some people think about analog. Kind of from your perspective, from the like software compiler perspective, how would you like to see the hardware to be for the on-device learning? Any specific requirements, specific architectures you think that may be the best?
From my point of view, and I think from our current projects, the main point for such hardware is not whether it's on memory or some NPU, some particular NPU. I think it's what I said is power consumption and ability to control it precisely for our needs. So to be able to save energy every moment. And currently, there are less of such architectures opened for publicity.
Right.
And yes, we found ARM SSU55 as very promising and as our main for current research. And I think this NPU is maybe very, very good and almost perfect. And of course, hardware, as I said, shall combine maybe 1 or 2 or 3 such NPUs with different computational resources, with different frequency, to be able to switch. When we need it, we will use a more powerful one. When we don't need, we'll use some very, very low power processing unit. So in our opinion, this is the main point for on-device learning and for edge AI purposes. Maybe it's some kind of more business point, but here we are.
So you're basically saying, if I summarize this, that you have a multi-core architecture with different cores that kind of can do different type of horsepower, and also to make sure that those cores are energy efficient. That's kind of what I heard you said. Yeah. Okay.
Yeah.
What about compute and memory? Because some people use also this type of architecture, like you have a compute and memory for certain very, very kind of low power applications, and then you have digital matrix multipliers that just do other things. Is it something like that would be of interest here as well?
Yes, of course. We investigated and maybe discussed some of these such solutions earlier, and if these solutions will provide some.
So maybe we can go through this Q&A. So I think the first question was on the TVM. Can optimization be done on U55?
Yes. actually, what we are done for TVM, it's specifically for integration of SoC 55. It was introduced by ARM initially. And yes, now, so in this year, we improved it, added more networks to be offloaded, fully offloaded. And yes, TVM is a great choice for SoC 55.
I think the second question is, can you share the best tools to choose the right hardware, which has good features like memory, computing power, specification for AI application? Kind of very, very broad question. But again, you've been working on this in this field for quite some time. Like, what would be your recommendation?
So maybe I'm not fully understand the question. The tools to choose the best hardware and software, as I understood this question. So in our from our experience, we just search for. First, we chose found NPU and TVM, and then so we use TVM.
Okay, so I think at this point, I think let's again thank you, Ilya and Grovety, for the presentation. The presentation will be available online. Yeah, so this is a list of sponsors we have, and you can acknowledge them one by one. So it's the Qualcomm executive, Sentient executive. Then we have Platinum sponsors, Sony, and the gold sponsors are Analog Devices, ARM, Edge Impulse, Infineon, and then Inotera, Microsoft, Renaissance, ST, Synaptics, and the silver sponsors are listed here. Okay, thank you again, and we'll see you in a week or so. Thank you.
Thank you. Bye.